All right. Hi, everyone. My name is Michael. So, containers. Yes. What even is this stuff? Look, I know how complicated the buzzword-laden world of containers can be. Trust me, I almost had 2 nervous breakdowns trying to write this speech. So, I'm here tonight to try and demystify it for you and lead you on the path to containerized glory. So, let's start at the top. What even is a container? Well, it's a technology that encapsulates an application or server with its dependencies so it can run in an environment isolated from other containers and the rest of the system. What does that mean? Basically, it's a way to bundle up an application along with everything it needs, be it code, runtimes, dependencies, everything. And then it gives you a way of running that in its own little world, separate from everything else, so it thinks that it's the only thing on the machine. It's great. So, next question, what is Docker? Well, Docker is just one of many tools that allow you to build, run, manage, and orchestrate containers. Like many, it's open source. However, there are 2 things that set it apart. For one, it's a all-in-one suite that handles the full container lifecycle. That means that basically anything you could possibly want to do with Docker, with containers, you can do with Docker. The other thing is that Docker is one of the main originators of what we think of today as containers. So that's why they're often the default choice. Not necessarily the best, but the default. It's also why often people refer to Docker and containers, as I will probably slip up doing tonight, interchangeably. Cool. So this is the container lifecycle. This is by no means an official image, but as you can see here, there are 4 stages to the container lifecycle. Yeah? There's the Docker file. It has no other name, I'm sorry. The image, the container, and the registry. So we're going to actually start in the middle with the container image because it is probably the most important part. It is the thing that we were referring to before when we say bundling everything up. This is the bundle. So it serves as a template of the application and the file system from which we spawn a container. We don't run the image directly. And once it's created, it cannot be changed. Yeah? It's locked in. It's immutable. And yeah, like we mentioned earlier, it contains everything that a container needs to run. And so we have containers. These are basically just what we call a running instance of the image. And if you really want to, for some reason, you can turn it back into a container by taking a snapshot of the file system. I've never done it, but maybe it's worth doing at some stage. So the question becomes, where do you get these images from? Well, one way is to build one yourself using Docker files. These are basically like recipes for how to build an image. It specifies a bunch of commands to be run as part of that build process, along with defining a bunch of image properties and metadata. And it also allows you to specify if you want to build based on another image or from scratch. Cool. Yep. Where do those images come from, though? Well, they come from an image registry. Docker Hub is the main public one, but it's totally possible to run your own publicly or privately, which is handy for sharing images amongst a team. And it basically is like a Git repository, but for container images. Cool. All right. So that's great and all, but we haven't really established why we would actually want to use these containers. There are plenty of reasons, in fact. For one, basically anything can be containerized, which makes it a universal platform. Being a way of bundling everything as well as running them in isolation makes them self-contained, which is super handy because it avoids things like dependency clashes. So if you've got 2 libraries that, 2 applications that need the same library but need different versions, you avoid any problems with clashes like this because they're running in their own worlds and you give them whatever version they need. This bundling also means that they're nicely portable, they're not tied to the operating system, so they're decoupled from infrastructure, and they're not really tied to any particular platform. There is a caveat to this, we'll get to that later. And because the images are immutable, they produce consistent containers that are going to run the same, perform the same across every environment, be it dev, test, or prod. And they're also really easy to spin up and shoot down when you don't need them anymore. Cool. And so if you do it right, you get lightweight, performant, scalable, modular, secure, uniform, disposable, immutable applications and containers. It's great. Fantastic. Woo! But how do you do it right? Like, what the heck does that mean? Let's talk about some best practice. But before we do, a disclaimer. Containers, the whole concept of containers is rather new, and Docker in particular is still quite juvenile, as seen from this recent portrait. It's all still in a state of flux, and so some 100% essential workaround today will be the height of bad practice tomorrow. And for that reason, the concepts we're going to cover tonight are really only high-level concepts, yeah? To get you in the right frame of mind rather than tell you exactly what to do and how to do it. That said, they are some of the most essential concepts, and you shouldn't go about breaking them until you know exactly what and why you're doing things. So let's start with the first one. And also worth mentioning, most of these come from a white paper published by Red Hat. All right, so the first one is the single concern principle, also known as, by me at least, the one thing principle. It says every container should address a single concern and do it well. So the mentality here is that each container should serve a single purpose. And usually this is done by having each container only contain one process, one executable. And that means that each server that's running as part of an application will need to be in its own container. Let's look at an example. So imagine that you have a web app running Node, backed by a Mongo database and some business logic handled by a REST API written in Python. To containerize this, you would break it into three containers: the Node container, the REST container, and the MongoDB container. Yeah? This means that when someone inevitably decides that they don't like Python anymore and they want to replace the REST API with a Java-based one, we can just replace that one part without touching any of the others and spin up a new container running our new REST API. It also means that if the reason we're doing that is because it kept crashing, those crashes will not have touched any of the other servers. They will not have affected any of the others because they're running in isolation. The other big benefit of this is it allows you to scale up on demand by simply deploying more of the container that you need at the time, rather than having to provision and spin up whole new virtual machines or hardware. You don't need to do any of that with containers. You just run more of the container that you need more of. So if your Node server is getting hammered, you run more of that Node containers and load balance them, which means a lot less overhead too. All right. Second principle is the process disposability principle. And it says containers need to be as ephemeral as possible and ready to be replaced by another container instance at any point in time. So containers are intended to only live a limited lifetime, and they're replaced at the first sign of trouble. And once they stop running, anything inside them is as good as gone. That's not to say that all containers need to be stateless. Like I already mentioned, you can totally run a database in a container. It just means that any data of any importance, any sort, needs to be stored outside of the container, be that database records, templates and data sets, configuration files, and even logs. This also has the side benefit of making all of your images and your containers smaller, which makes them easier to distribute. So how do we make these things outside of our container? Well, there are two things, volumes and bind mounts, and they're both kind of like a weird, complicated symlink. They allow you to map a folder inside a container to some sort of storage outside of the container. So in the case of volumes, it's controlled by the containerization software, so usually Docker, and you cannot directly access the storage. You can't do it. You're not supposed to do it. All that matters is that when you start up a new container, you reattach that volume and everything that was there previously will still be there this time. Great. The other option is bind mounts, and these allow you to directly map a folder on your file system into the container, which means that you get bidirectional communication through this container and any files in there. So you can see what the container is doing and the container can see what you're doing, which is handy for things like backing up files or hand editing configs while you're, still debugging your container. All right, third principle, the image immutability principle. This says, once built, container images are not expected to change between different environments. The idea here is that images shouldn't need to be modified to run on different platforms. Instead, any environment-specific configurations should be stored externally, like we previously mentioned. This allows the same image to be used in dev, test, prod without modification. Cool. And the fourth principle is the self-containment principle. And this says that a container should contain everything it needs at build time. So I know I already mentioned it, but just so we're 100% clear, images cannot be changed once they are built. And once a container is spawned, it also cannot be changed. So if you need to change a container for some reason, then you need to go and change whatever needs changing in the image by changing your Docker file probably, rebuild the image, push over this container, and bring up a new one. Or probably in the other order. Yeah, there's no altering things inside, you just need to replace it. And, yeah, sure.
Sorry, so yeah, how big is the image that you have to upload now once you've built it?
Well, it's going to be as much bigger as your change has been. It's going to be a whole new image.
But you're going to have to upload the whole image.
Yes. So because the image is totally self-contained, you can't modify things about it, so you're uploading a whole new image. But the aim of the game here is that your images should be well less than a gig. They should be in the less than hundreds of meg size. That's what most of the ones available on like Docker Hub are, but if you're not doing things well, then it's possible they'll be bigger. Yep.
Thanks.
No worries. Okay, so as self-contained as a container is, there's still one aspect of the host machine that the container relies on, and that's the kernel. No matter how many dependencies a container includes with it, it'll eventually still have to make calls down to hardware. Yeah? And that means making calls through the kernel. So that means that a container is only as portable as the kernel and the architecture it was built for. Now this sounds really bad, but in most cases it's not that big a deal, but it does add a little bit of complication to things. So the majority of container images in the world today are built to run on the Linux kernel. This is because the original technology that containerization is based on came from that kernel. That's great and all for anyone in the room running Ubuntu right now, but what about everyone running Windows or Mac OS? Well, if you're using Docker at least, it should automatically set up a virtual machine for you running Linux, and it will run all of your containers inside of that. Unless you're running Windows containers, which can be run natively on Windows Server at least. So that's okay. No such luck for Mac OS though, unfortunately. So you're stuck with virtual machines. This kind of proves the point about wanting to have your image be the same across dev and test and prod. This is not a situation you want in a production environment. You don't want to run your virtual machine inside, your container inside a virtual machine. It's unnecessary and it's painful. But for a development environment, that's perfectly good enough because it's going to perform the same there as it will on your production server. All right. So as you can see from all this, containers are best suited to a particular application architecture, namely microservices. So if your application consists of a bunch of small services communicating over a network, then it's perfectly suited to containerization. But if it's mostly self-contained, it doesn't communicate with anything, then it's probably a monolith. And while it's totally possible to containerize it, it means you have to just stuff the whole thing into a single container. And that's probably going to break some of these principles, and you're probably not going to get most, if not all, of the benefits that we just talked about. Yep. So microservices sound cool and all, but it sounds pretty hectic to try and manage a whole ton of tiny little services communicating all over the place. So what's the solution for this? That's where Kubernetes comes in. Kubernetes, also known as K8S, because K, 8 letters and then an S, is a system for automating deployment, scaling, management of containers. So it's designed to orchestrate containers over a number of physical or virtual machines as a group, and it allows you to scale them up and scale them down automatically. It groups the containers into pods, and so if there's like pairs of containers that need each other, like a server and a database, they will come up together, so there's always enough of whatever it needs. They also come with a bunch of cool features like automated failover, so if a server goes down, it will start up a new one to replace it, or if it stops responding, it will kill it and replace it, and load balancing, and it'll scale up and scale down based on not just load, but also resource availability. Yep. So, my final word of warning. While containers can be a complicated and messy thing at times, they have so much power and potential for security, performance, and flexibility. But with great power comes great responsibility and an even greater chance of blowing your own foot off. That's why I highly encourage you all to go out and try them yourself, but definitely not in a critical environment. I also recommend you do some further reading from particularly reputable sources like Docker or Red Hat, as there are a lot of outdated misinformation out there, especially around Docker. So these are some of the sources that I based this talk on. We have the Red Hat white paper here, the Docker Getting Started guide, which is much improved since I first looked at it, thank goodness. This is a presentation about Docker storage and how that works, and about how virtual machines versus containers work, which is handy. So thank you for listening, and any questions?